What do you know about a triangle? Yes, the most simple polygon with 3 vertices, 3 sides, and 3 angles. However, it can be of many shapes and sizes: tall, short, upright, or blunt with an obtuse angle, sharp with an acute angle. Other than that, it can give us many useful information and has many interesting and amazing properties, of which we are going to tell. But before we start, we would like to ask you to give us a like and subscribe our channel. Now let's begin. The story of triangle. Triangles and. What is a triangle? Everyone knows. A triangle has 3 sides and 3 angles. However, there are many family members, of which there is the scalene triangle with all angles acute, that is smaller than 90 degrees, and all sides differ. Then next comes the isosceles triangle, which has 2 of its sides equal, and the equilateral triangle with 3 sides equal and 3 angles equal to 60 degrees. However, the equilateral triangle has many other special properties and features which we will talk about later. After that is the right angle triangle, which has an angle equal to 90 degrees. Then the right angle isosceles triangle, having a right angle included between 2 equal arms. Lastly is the obtuse triangle, which has an angle larger than 90 degrees, and the obtuse isosceles triangle with the obtuse angle included between 2 sides of equal length. So after seeing the various members in the triangle family, let's look at the angles and sides of a triangle. A triangle has interior angles and exterior angles. The angle included between 2 arms is called the interior angle. So it's this one, and this one. And that angle here outside the triangle is the exterior angle. However, no matter what triangle it is, the sum of its interior angles, here, angle A plus angle B plus angle C is equal to 180 degrees. You can see it here. Here we see in this triangle ABC, the small green triangle here on the left is equal to the blue one, this here on the left. So it's this one on the top, and this one down here, and this blue one on the left, and this green one here. If we flip them up, you see that they just cover up each other. So alpha is equal to A. Alpha is equal to angle A. You see, this is alpha, and this is A. And beta is equal to angle B. This is B. This is beta. And gamma is equal to C. This is C. This is gamma. However, you can see that here, alpha, beta, and gamma sums up to 180 degrees because they are adjacent angles on a straight line. Therefore, angle A plus angle B plus angle C also sums up to 180 degrees. We call this angle sum of triangle. Now, after talking about the interior angles, we now come to the exterior angles of a triangle. Here, alpha, beta, and gamma are the exterior angle of triangle ABC. Here, if we move this green pointer here, this is alpha, this is beta, and this is gamma. And here we can see that alpha, beta, gamma sums up to 360 degrees because the pointer has just turned a complete round. It comes back to the very starting position. Therefore, alpha plus beta plus gamma is 360 degrees. That means the sum of these three exterior angles of the triangle will be 360 degrees. We call this sum of exterior angles. So exterior angles of a triangle. And here coming up is something more about the exterior angle of a triangle. And in the figure here, we see in this triangle ABC. ABC are the interior angles and X is the exterior angle. Here we see that A plus B plus C is 180 degrees because the angle sum of triangle. And B plus X is also 180 degrees because they are adjacent angles on a straight line. Therefore, we have A plus B plus C is equal to 180 degrees and equal to B plus X. So if we cover up B, or we pick B up from both sides of the equation, we have A plus C is equal to X. A plus C is equal to X. That means this is A and this is C. The sum of these two interior angles, A and C, will sums up to this exterior angle X. Here, A and C sums up to X. Therefore, for a triangle like this, we will have the sum of these two interior angles sums up to this exterior angle. We call this exterior angle of triangle. So after catering for the angles of a triangle, we now come to the sides. We have the isosceles triangle here. This isosceles triangle have two equal sides. You see that this is AC and this is BC. So this one, AC and BC. This isosceles triangle here, if we drop a perpendicular from C to AB, we have AC equal to BC, and CD is common. Angle CDA equals to angle CDB. Then these two triangles will be congruent, RHS. You see that they're exactly the same. And the corresponding angles A and B also the same. This is A, this is A, and this is B. Therefore, for an isosceles triangle, we will have the base angles equal. We call this base angles isosceles triangle. Then after talking about the isosceles triangle, we now come to the equilateral triangle having three sides equal in length. Let's look at this triangle, this equilateral triangle ABC. If we look in this way, it is an isosceles triangle with angle B equals to angle C. And if we look in this way, we have it is also an isosceles triangle, and angle C equals to angle A. If we look in this way, angle A equals to angle B. Therefore, these three angles are equal, and the sum is 180 degrees because of angle sum of triangle. So each angle is equal to 180 divided by 3, that is 60 degrees. Therefore, in an equilateral triangle, all sides are equal, and so are all the angles, of which they are 60 degrees each. After looking at the angles and sides of a triangle, let's see something new, the centers. There are some special points in a triangle, we call them centers. Have you heard of the 9-point circle? But today we are just going to discuss two of them, the oval center and the in center. So what is meant by the oval center and what is meant by the in center? Here, in this triangle PQR, the perpendicular P, this is the perpendicular dropping from P. So this one from R and this one from Q. We can see that the three perpendiculars will meet and intersect at a very single point X. We call this concurrent. And this is the oval center of this triangle PQR. Then comes the in center, which are the point of intersection of all the angle bisectors of a triangle. Here we see that this is angle R and this is half of angle R. So this is half of R. So this is the angle bisector. And this is angle S. So this half of angle S, this is 1/2 of S, and so this one. Therefore, this is the angle bisector of S. And so this one, this is 1/2 angle T, and so this one, 1/2 of angle T. So this is the angle bisector of angle T. We see that here in triangle RST, the angle bisectors intersect meet at this point Y. That means these three angle bisectors are concurrent. And this point Y is called the in-center of triangle RST. This is what is meant by the in-center. However, for an equilateral triangle like this one, ABC, this is the ortho center, X. This is the intersection of the three perpendiculars. And this is the angle bisectors. And this point Y is the in-center of triangle ABC. You see that the ortho center of triangle ABC coincide with the in-center Y. They are actually the same point. So we can see it this way. This is the in-center Y, and it coincide with the X, with the ortho center X. Therefore, we can say that for an equilateral triangle like this ABC, the ortho center and the in-center coincide and become one point, like this. Therefore, for an equilateral triangle, the in-center and ortho center unite to one point. And an equilateral triangle is so unlike a one in the triangle family that we can tell some special trigonometric ratio by just a glance at it. Let's look at this equilateral triangle here, which has two units, which has sides of 2 units in measure. And here AM is the perpendicular, or we can say that this is the perpendicular bisector of BC dividing angle A into 2 halves, with this side 30 degree and this side 30 degree. And here we can see that from this figure, tangent 60 degree is equal to root 3 over 1. According to the Pythagoras theorem, we can see that the square of this is the square of root 3 is 3, and this is 1. When 3 plus 1 is equal to 2 squared, that is 4. Therefore, tangent 60 degree is equal to root 3 over 1, that is root 3. And tangent 30 degree is equal to 1 over root 3. Also, sine 60 degree is equal to root 3 over 2, and sine 30 degree is equal to 1 over 2. There is 1 half. And cosine 60 degree is equal to 1 over 2. There is 1 half. And cosine 30 degree is equal to root 3 over 2. So we have discussed triangles, angles, and sides, and how to find some features of an equilateral triangle. Then, how about the area? That's simple. The area of a triangle is equal to 1/2 the product of its attitude and base. Yeah? If H is the attitude and L is the base, then its area is equal to 1/2 HL. But how does it come about? Here we see that in this triangle AXB, if we cover this up, cover up this half, we can see that the area of this white triangle here, this is the area, and it is equal to the area of this green triangle. This is also the area of this green triangle. So the area of these white triangles is equal to 1/2 of this rectangle here and here. So this one, the area of this white triangle, this is the area, and this is also the area of this blue triangle. So on the whole, the area of this triangle AXB is equal to 1/2 this rectangle ABCD. And as the area of the rectangle ABCD is the product of H and L, therefore the triangle of this ABX is 1/2 HL. That means the area of a triangle is equal to 1/2 the base, the product of the base and the height. However, there are other ways of finding out the area of a triangle. One is the famous Heron's formula. And for the Heron's formula, we need to know the length of the size of the triangle when we use it. We are not going to show the proof here, but just mention how to use it. Here, in this triangle ABC, the side opposite angle A is A, and the side opposite angle B is B. So the side opposite angle C is C. And S is equal to 1/2 the sum of A, B, and C. That is, S is 1/2 the perimeter. Then according to Heron's formula, the area of the triangle will be the square root of S times S minus A times S minus B times S minus C. Is that all? Not quite. There is also another formula for the area of a triangle. It is half the product AB sine C. As shown in the figure here, H is the altitude of the triangle. That is the height, and B is the base. So the area of the triangle is equal to 1/2 the height and the base of the product, the height and the base. That is 1/2 HB. And since H over A is sine C, therefore A sine C is H. And BH is equal to B A sine C, because H is A sine C. So the area of a triangle ABC is 1/2 AB sine C. Wow, do you need a break? There's something more we are going to tell. After going through the angles, the size, and the area, we would like to introduce a concept of congruence and similarity. What is meant by congruence? If two figures are said to be congruent, that means the two figures is the same in shape and size, and we can cover it up with one another. And for triangles here, when two triangles are said to be congruent, that means their three corresponding sides are equal, and their three corresponding angles are also equal in measure. That is, they're exactly the same in size and shape. And also they can cover each other. here we can see that for these two triangles, AB, this is AB, and this is DE. So AB is equal to DE, and here, so this is BC, this is BC, and this is FE. So BC is equal to FE. And this is AC, and this is DF. So AC is equal to DF. These two triangles have their three sides equal. And we can see that here, the three angles are also equal. And these two triangles are also of the same shape and size. So, these two triangles are congruent. And we can see that there are 5 sets of determining factors for congruence of triangle. Namely, they are SSS, SAS, ASA, AAS, and RHS, where A stands for angle and S stands for side. And R stands for right angle, H stands for hypotenuse, also S stands for side. Let's see the first one. When the length of the three sides of a triangle is fixed, it is not possible for us to move the sides without breaking the triangle. Therefore, if two triangles have their three sides equal to measure, then the two triangles are said to be congruent. Here, let's look at these two triangles ABC and DEF. We have the side AB equal to DE, and also this side BC equals to EF, and this side CA equals to FD. So they have three sides equal. So we say that these two triangles are congruent. You see that therefore they are of the same shape and size, and they can cover each other. Therefore, triangle ABC, congruent triangle DEF, side, 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 with their corresponding vertex in the same order. Situation 2. When a triangle has its base fixed and the two adjacent angles also fixed, you cannot change the shape of it without movement of the arms. That is, changing the angles or the length of the base. There is changing the angles or the length of the base. There is only one outcome. Therefore, if two triangles have their base the same in length and the two adjacent angles equal in measurement, then the two triangles are said to be congruent. Here we can check this out for triangle ABC and DEF. Here we have, this is angle A equals to angle D, and angle B equals to angle F. So we have two angles equal. Then how about the side in between? So here, AB equals to DF. So we have angle side angle. Therefore, we can say that triangle ABC congruent triangle DEF. You see that they are exactly the same in size and shape. So we can write it here. Triangle ABC congruent to triangle DFE, with the vertex in the corresponding order, and we cannot mix them up because A correspond to D and B correspond to F and C correspond to E. Now we come to the third one, SAS. We can see that from the figure, whenever the two arms of the triangle are determined in length, we cannot change the shape of each without changing the angle in between. Therefore, if two triangles have their two corresponding sides equal and the in-between angle exactly the same, the two triangles are congruent. This is the situation here below for triangle ABC and triangle DEF. Here we see that this arm AC is equal to DF, and also another arm AB is equal to DE, and the in-between angle A equals to angle B. So these two triangles ABC and DEF, they are exactly the same in shape and size. Therefore, triangle ABC congruent triangle DEF, side angle side. Now we come to the fourth condition, AS angle side. When a triangle has two of its angles fixed and adjacent sides determined in length, the triangle will have its shape and size determined. No other triangles can be formed without changing either the angles or the length of the fixed side. Therefore, if two triangles have two of their corresponding angles equal and one of the adjacent sides also equal in length, the two triangles are congruent. This is the case in triangle ABC and DEF. Here we have this angle A equals to angle D, and angle C equals to angle F. So we have two angles equal, and this adjacent side AB and DE are also equal. So we have AAS, angle side. So we see that these two triangles are congruent. They are exactly in shape and size. Therefore, we have triangle ABC congruent triangle DEF, AAS. Then we come to the last case, and this last case is a special case of SSA. Here we see that we have seen the case of side, angle, side, angle, side, and angle, side. Now then, how about side, angle? Let's see this one. Here we have this side AB fixed and this angle firm. Then how about this side AC? Yes. we see that if we have AC fixed, we can have two choices. One is this one, AC1, or we can have it like this, AC2. Therefore, there are two positions for us to put this side BC. We can put it here, or we can put it here. The triangle in the figure has a fixed arm AB and a fixed angle A. And for the other arm BC, we can have two choices. So there are two positions to choose. Therefore, we will create two different triangles, ABC1 and ABC2. And it is very clear that there are two different triangles. And however, these two cases will come to one unique one. Will come to one unique BC if BC is not like this and like this, and actually BC is like this. That is, BC is perpendicular to AC. If this is a right angle, then we can have only one case. Like this. And we call this case RHS, a right angle, hypotenuse, and side. This is the side. This is the hypotenuse. And this is the right angle. We call it a RHS condition. That means when two triangles have a RHS condition, these two triangles are congruent. That means they have the same hypotenuse. Also, one equal side and one right angle. Therefore, in this case, triangle ABC, congruent triangle DEF. Now we come to the very last topic. We will discuss about similarity. Here, what is similar? It means two figures. It means the figures of It means two figures are of the same shape. But can we tell you more exact? Yes. It means that their corresponding sides are proportional and all their angles are equal if they have. Here we can see that these two pentagons are similar. So are these two triangles and these two rectangles. However, in triangles, proportional sides will also have their proportional angles equal at the same time. Therefore, to prove triangles are similar, we need to prove the following condition exists. The first is AAA, three angles equal. The second is SSS, three sides proportional. And the third is SAS, two sides proportional and include angle equal. Here we look at the first one, the AAA. That means three corresponding angles equal. If two triangles have all their corresponding angles equal, then the two triangles will have the same shape, but their size may vary. Let's look at these two triangles, where angle A here, angle A equals to angle D, and angle B equals to angle E, angle C equals to angle F. You see, this is triangle DEF. And here we can see that when one of the corresponding sides change, or maybe we can try this one. When one of the corresponding sides change, the other two will change in accord. You see, if this side gets longer, so are these two sides, keeping all three angles equal. Here, this angle, the angle haven't changed, but the side has changed. So this one. So you see that in this change, when one side change, the other two sides will change in accord, and keeping the three angles equal. That means these two triangles are similar. And this is AAA. That means that all three corresponding angles are equal. Now here we have come to the second case. That means all three cross SSS. That means all three corresponding sides are in proportion. How are they in proportion? Here we see that for example, here, if one side is double, if AC is doubled, here is AC. So this is 2AC. So are this one. This is BC, and also these are BC. So this is 2BC, and this is AB, and so this one, AB. Therefore, in this triangle, this is 2AB, 2AC, and 2BC. The side is doubled, or we can say that here, if the side is halved, this is 1/2 AC, this is 1/2 BC, this is 1/2 AB. If one side is half, so are the other two. Therefore, we have AC over the and here, if we have AC over DF equal to CB over FE, CB over FE, the corresponding size, the ratio is the same, and BA over ED, they have also, these three sides have the same ratio. Then these two triangles, you see that the angles are equal. Angle C, and this angle C, this angle C, and this angle B, and this angle B. The three angles are also equal. That means these two triangles are similar. And for the last one here, we come to the very last part, the SAS. It means if two triangles have their two corresponding sides in proportion and the in-between angles equal, then these two triangles are similar. Here we see that if these two triangles are similar, then the in-between angle A, is equal to angle D. And that you see here. I'll take this out. If one side change, if one side, this side AC is shortened, so are AB. You see that? Keeping all three angles equal. So here we have AB shortened, and so are AC shortened at the same time in a chord. Therefore, we will have AB equals to AB over DE equals to AC over DF, and angle A equals to angle D. In this case, we call this SAS, sine angle sine. It means that they have two corresponding sides in proportion, and the in-between angle A and angle D, the same. Then we call this a SAS condition. So after seeing so many properties and features of triangles, we know that the story of triangle will never end. And there are actually so many to tell about them that we need to have a break here. But before we say goodbye, we will once more like to ask you to give us your support and subscribe our channel. Thanks much for your watching.